In this video, we're going to have a look at why time slows down as you approach the speed of light. Before we do this, there are two very important facts that we need to have a look at. The first one is Galileo's principle of relativity. Galileo was an Italian physicist, and he said that all steady motion is relative and cannot be detected without reference to an outside point. So, to think about this more clearly, imagine you're sat on a train that's travelling along. You can look out of the window and you can see trees and houses flying by, so you know that you're moving. Galileo's principle of relativity says that if all the windows were suddenly blocked off and you couldn't see outside, then you would have no way of knowing whether you're moving or you're stationary or what direction you're moving in. To be able to know these things, you have to be able to look outside the train and have reference to something else that's moving relative to you. This is a very important point which we'll come back to later. The second thing we need to know is that the speed of light is constant. In 1887, two physicists called Albert Michelson and Edward Morley showed this in an experiment. They found out that it didn't matter if light was travelling with the Earth's direction of rotation or against it, the light was still travelling at the same speed. We know this speed to be 299,792,458 metres per second. As this is such a long number, we generally denote it by the letter c. We will use this letter later. At the beginning of the 20th century, a young German called Albert Einstein was thinking about the speed of light. He imagined he was sat in a spaceship travelling at the speed of light while looking in a mirror. Light bounces off you and travels to the mirror where it is reflected back to you, allowing you to see your reflection. Einstein wondered if the spaceship is travelling at the speed of light, hence the mirror is also travelling at the speed of light, surely the light from you can't actually reach the mirror. Because it can't catch it, you won't be able to see your reflection. But no, Galileo suggests this is wrong. So this would contradict Galileo's principle of relativity. If you couldn't see your reflection, then you'd know that you were moving at the speed of light, even though you couldn't see outside the spaceship and have no reference to anything outside of the spaceship. If this can't happen, then what is it that's actually happening? Einstein's second thought was that maybe light leaves you at twice the speed of light, so that it can catch up to the mirror like usual, and then you'll be able to see your reflection. But no, that's not possible either. The speed of light is always the same. We can't just add on more speed of light so that it can catch up with the mirror. Therefore, it must be something else that's changing. Well, speed is equal to distance divided by time. So if it's not the speed of light that's changing, it must be time and distance. Now, to work out how much the time is changing by, we're going to do another thought experiment. Imagine a light clock. The light clock works by emitting a pulse of light, which then hits a mirror, bounces back to the clock and hits a sensor. When the pulse of light hits the sensor, you hear a click. Another pulse of light is then emitted, it hits the mirror and bounces back, and you hear another click. Now imagine this light clock is in a spaceship that's travelling along at a speed that we're going to call v meters per second. Notice in the diagram that the light is travelling perpendicular to the direction of the travel of the spaceship. This is very important. Now imagine the same light clock, but this time imagine you can see it from outside of the spaceship. You're stood still watching the spaceship travel past, so the light clock emits its beam of light, but by the time the beam has reached the mirror, the spaceship has moved, hence the mirror and the clock have also moved. The light then bounces back again, but the spaceship has carried on moving, so the clock has also moved. You can see in the diagram that the light now appears to be taking a diagonal route to the mirror and back again. It appears to you, the stationary observer, to be travelling further, but we know that its speed hasn't changed. It's still travelling at the speed of light, so it must be taking longer to do its journey. You, the observer, would hear a longer gap between the clicks, therefore the clock seems to have slowed down. To work out how much it has slowed down by, we're going to do a bit of algebra. So we're going to let v equal the speed of the spaceship. T dash is going to be the time between the clicks for the person in the spaceship, and t will be the time between clicks for the observer outside of a spaceship. Finally, c is the speed of light. So, on the ship, This is what the person in the spaceship sees. We're going to call the distance between the light clock and the mirror L. Time is distance divided by speed. The light has to go to the mirror and back, so it's travelling 2L. Therefore, the time it takes is 2L divided by c. Now for the person observing from outside of the spaceship, the light travels further. We're going to call this diagonal distance h, and we're going to say that the ship has moved a distance of d in between clicks. The light has taken a triangular path due to the clock's movement. The time it takes would now be 2h over c, the distance divided by the speed, and the clock has moved a distance of d, which must be equal to v, the speed of the spaceship, multiplied by t, the time between the clicks. Now looking at the diagram of the moving time clock, we can see that h is the hypotenuse of a right-angled triangle with sides L and half d. Using Pythagoras' theorem, we get that h squared is equal to the square of half d add L squared. But we've already worked out that t is equal to 2h over c. Rearranging this gives us h equals a half ct. We also know that d is equal to vt, and we know that t dash is equal to 2L over c, which rearranges to give L equal to a half ct dash. Now we're going to put these three values into Pythagoras' equation to give us this equation here. A half ct all squared equals a half vt all squared plus a half ct dash all squared. We've now got an equation linking the two times together, but we're going to need to tidy this up a little bit. The first thing is to multiply both sides through by 4 to get rid of the half squared. Now if we square our brackets, we get this, c squared t squared equals v squared t squared plus c squared t dash squared. Now take v squared t squared away from both sides. You can see that both terms on the left have got t squared in them, so we're going to factorise that out and then divide by c squared minus v squared. And then finally, we're going to divide top and bottom of our right-hand fraction by c squared to give us t squared equals t dash squared over 1 minus v squared over c squared. But actually, we wanted an equation in t, not t squared, so let's square root both sides, and there we have it. The time between the clicks of the observer is equal to the time between clicks for the person in the spaceship divided by the square root of 1 minus the speed of the spaceship squared over the speed of light squared. Let's use our new formula in an example. An astronaut leaves Earth travelling at 0.7 times the speed of light. After 5 years have passed on the spaceship, so the astronaut is 5 years older, how much time has passed on Earth? Well, here's our equation. We know that t dash, the time for the astronaut, is 5 years. We know that v, the speed of the spaceship, is 0.7 times the speed of light, or 0.7c. So let's substitute them in. We can then square the brackets at the bottom of the fraction there to give us 0.49c squared. Cancel out those two c squareds to give us t equals 5 over the square root of 1 minus 0.49. This equals 5 over the square root of 0.51, which gives us an answer of approximately 7 years. So the astronaut is 5 years older. Everybody else outside the spaceship is actually 7 years older. Time has slowed down for the astronaut. If you've enjoyed this video, don't forget to subscribe to the Doing Maths channel or check out some more of my videos by clicking on the links here.